Welcome to this explainer. You know, we usually think of the ground right beneath our feet as completely solid, permanent, and, well, unmoving. But the truth is, the Earth's surface is actually this constantly shifting canvas, and it is being sculpted right under our noses. Today, we're going to explore exactly how that happens. It really is a giant canvas, constantly being carved by these relentless natural artists. It's a metaphor, sure, but it perfectly captures what's happening geologically out there. We're going to look at rivers acting as these broad stroke painters, groundwater operating as a hidden acid etcher, and massive glaciers behaving like incredibly heavy bulldozers. All right, so here's our game plan for today. First, we'll see how running water shapes the surface. Then, we'll dive down into the hidden world of groundwater. After that, we're heading up into the mountains to look at glaciers, Earth's ice bulldozers. And finally, we'll sort through the fascinating debris those glaciers leave behind. Let's jump right into Section 1. Running water shapes the surface, the broad strokes of sediments. Think of rivers as the painters of the Earth. As they rush down from high mountain peaks toward the sea, they carry just absolutely incredible amounts of sediment, forcefully spreading broad strokes of material all across the landscape. Now, there are two entirely different ways rivers actually dump this load. When steep, heavy mountain streams suddenly hit a gentle, flat gradient on land, we get alluvial fans. The river essentially just drops everything at once because the load is simply too heavy to carry anymore. The result? A messy, unsorted, cone-shaped deposit of very coarse material. But when that same river dumps its load into the sea, we get deltas. Because of how water dynamics work in the ocean, this dumping is highly sorted and clearly stratified. The heavy, coarse materials settle out first right near the shore, while the fine silts and clays are gracefully carried way farther out into the water. As we move further down the river's path, we journey across the floodplains. The river travels in its active floodplain, that's the constantly shifting bed of active deposits, while leaving behind an inactive floodplain up above the banks, which holds on to older flood and channel deposits. Now, as the river repeatedly floods over time, it acts like a builder, depositing coarse materials right along its edges to create these low, linear ridges we call natural levees. And, rivers rarely flow perfectly straight, right? They swing back and forth like a pendulum, forming loop-like channel patterns called meanders. As the water rushes through these loops, it gets super dynamic. It aggressively undercuts the outer convex banks and then smoothly drops uniform sediments, known as point bars, on the slower inner concave side. It's just this continuous, incredibly beautiful cycle of carving out and painting over. Moving on to Section 2, the hidden world of groundwater, the subterranean acid etcher. Okay, so we've seen what water does on the surface, but now let's talk about a sculptor that operates completely out of sight. The crucial thing to understand here is that groundwater doesn't rely on brute mechanical force like a rushing river does. Instead, it relies on chemistry. When groundwater moves through regions rich in limestone or dolomitic rock, basically rocks heavily packed with calcium carbonate, it acts exactly like an acid etcher. Through the chemical processes of solution and precipitation deposition, it literally dissolves the rock away from the inside. We call this entirely new, often totally alien-looking landscape karst topography. So what happens when the solid ground beneath you is being chemically eaten away by this unseen etcher? Well, you get a doline. That's the scientific term for the dramatic collapse sinks, or sinkholes, that can suddenly dot the surface of a karst landscape. It's literally just the surface caving in, revealing the massive chemical hollows that were carved out directly beneath it. And that brings us to a really fascinating question. We've talked a lot about liquid water, both on the surface and underground. But what moves mountains without a single drop of liquid water? Take a second to just think about that. Which brings us perfectly into Section 3, glaciers, Earth's ice bulldozers, the heavy mountain carvers. These heavy mountain carvers move purely through the relentless force of gravity, and the erosion they cause, it's absolutely enormous. It's driven entirely by the intense friction and the sheer crushing weight of solid ice, grinding directly against bedrock. But before we look at exactly how they carve, I want to ground this in reality for a moment, because these ice bulldozers are actually intimately connected to the rivers we were just talking about. Ice feeds the rivers. For example, meltwaters from under the snout of the Gangotri Glacier actually feed the Bhagirathi River. Meanwhile, the Alkapuri Glacier feeds the Alakonda River. These two massive glacially fed water sources eventually join up at Deoprayag to form the mighty Ganga River. So these frozen giants are literally the source of major life-giving river systems. So where does all this glacial mountain carving actually begin? It starts with the cirque. As ice accumulates way up high on mountaintops, it begins to move down, cutting these deep, long, wide troughs with incredibly steep, sometimes perfectly vertically dropping, high walls at the head and the sides. Basically, imagine a massive, sheer bowl gouged right out of the peak by the ice. Now picture how a mountaintop transforms into one of those dramatic landscapes we all recognize. First, the accumulated ice cuts those deep cirques. Next, those steep cirque walls undergo what geologists call headward erosion, which basically means they actively erode backward, deeper into the mountain. Now imagine 3 or more of these glaciers radiating outward from a single mountain peak, all eroding backward until their cirques finally meet right in the middle. The result? A high, incredibly sharp-pointed peak known as a horn. Iconic peaks like the Matterhorn in the Alps or Mount Everest in the Himalayas. They were formed exactly this way. And the divides between these cirques slowly narrow down into these incredibly sharp, saw-toothed ridges that we call arêtes. As these absolute bulldozers grind down the mountain, they completely change the shape of the valleys they pass through. Remember how a river carves a sharp V shape? Well, a glacier leaves broad, U-shaped floors with smooth, steep sides. These U-shaped troughs can be littered with debris or gouged-out rocky lakes. Sometimes you'll have smaller glaciers feeding into the main one, and they leave behind hanging valleys elevated way up high above the main trough floor. And when these incredibly deep glacial troughs eventually meet the ocean and fill up with seawater, which happens a lot in high latitudes, we get fjords. Finally, let's wrap up with Section 4, the debris glaciers leave behind, sorting the leftovers. All right, so eventually the ice melts and retreats. What on earth happens to all that crushed up rock? Well, when ice drops debris directly, we get what's called glacial till. Because ice doesn't sort things by weight the way water does, till is just this completely unassorted, chaotic mix of coarse and fine debris. And because it was basically just dragged and dropped, the rock fragments are sharp and angular. But when the glacial-fluvial meltwater streams wash that debris away, we get outwash deposits. Because water is doing the moving this time, the materials are roughly stratified, sorted, and the edges of the rock fragments actually get smoothed and rounded out. This debris piles up to build massive landscape features called moraines. They're essentially just long ridges of that glacial till we just talked about. Picture the journey of the ice through a valley. Right at the toe, or the very end of the glacier, it dumps a terminal moraine. Along the outer edges, running parallel to the valley walls, it builds lateral moraines. If the glacier melts and retreats super rapidly, it leaves an irregular sheet of till draped across the entire valley floor called a ground moraine. And this is pretty cool. If 2 flowing glaciers happen to merge together, their inside lateral moraines combine to form a medial moraine, running right down the dead center of the newly combined valley. Okay, this is one of my favorite little microstories in geology. Imagine the summer heat starts melting the top of the ice. That water seeps down through holes and cracks until it hits the ground. Then, actual streams begin to flow in channels entirely underneath the heavy ice glacier. As they flow, coarse boulders and blocks settle in the stream bed beneath the ice. Finally, when the ice completely melts away years later, what's left behind? It's not a valley, it's a winding, sinuous ridge of rocks standing above the plain. We call this an esker. Just a couple of final touches from our glacial artist to mention: drumlins and outwash plains. Drumlins are these smooth, oval-shaped ridges made of till. What's amazing about them is their long axes align perfectly parallel to the direction the ice was moving. They are literally like giant geological footprints pointing the way. And spreading out far beyond the foot of these mountains are the outwash plains, massive, broad, flat areas built from layers of gravel, silt, and sand that were carried away by the meltwater. We've covered the painters, the hidden etchers, and the massive ice bulldozers. So I want to leave you with this thought. Next time you stand before a jagged mountain peak, a winding river, or a deep U-shaped valley, ask yourself, which master sculptor carved the canvas beneath your feet? Keep looking at the world closely, and I'll catch you in the next explainer.